So, today I shall explain to you in slightly greater detail how when we look at a quantum filtering problem corresponding to a Hamiltonian system with noise, then the resulting filtering problem, namely Biliarching's filter when formulated for this system, is actually a Kushner-Kalyanpur filtering equation with some small correction terms coming in powers of Planck's constant. I shall derive up to order Planck's constant, linear orders in the Planck's constant, the exact corrections which the Biliarching filter gives as compared to the Kushner-Kalyanpur filter, provided we interpret the density, joint density of momentum and position as a Wegner-Wille distribution, because position and momentum are not simultaneously measurable in quantum mechanics, they do not commute. So, we can talk only of a Wegner-Wille distribution or a Wegner distribution for the density of q and p, such that the marginal with respect to q is equal to the actual probability density of q and the marginal with respect to p is equal to the probability density of p. So, we are given a Hamiltonian system described by equations of the form dqit is equal to dou h, say I take just one degree of freedom, qp by dou p and dp dpt is equal to minus dou h qp by dou q dt minus some other, say some drift term you may have, or let us say you do not have, if you have a drift term, if you have a damping term, then this term is represented by this plus some sigma square by 2 plus sigma times dbt, where bt is standard Brownian motion. This is the system of stochastic differential equations which describes the motion of a particle having Hamiltonian HQP and subject to damping and diffusion. So, if you look at PQP, the joint density of q and p, it satisfies the Fokker-Planck equation, namely del by del t of this is equal to minus of dou by dou q of p into dou h by dou p plus dou h by dou q into dou p by dou p plus gamma times dou by dou p of p into p plus sigma square by 2 dou square p by dou p square. This is the Fokker-Planck diffusion equation. This is nothing but the Poisson bracket. This can also be written as dou p by dou t is equal to the Poisson bracket between h and p. So, you can say minus of the Poisson bracket between h and p dt plus a drift term which is plus gamma. Plus gamma times dou p into p by dou p plus sigma square by 2 dou square p by dou p square. We want to derive such an equation from quantum mechanics, and this is the classical Fokker-Planck equation for a Hamiltonian system in noise and damping. H comma p is the classical Poisson bracket between h and p, namely h comma u comma v for two observables in class is a Poisson bracket which is dou u by dou q into dou v by dou p minus dou u by dou p into dou v by dou q for a single degree of freedom. So, that describes the Fokker-Planck equation for the joint density of position and momentum. In the quantum mechanical situation, you have actually also called a stochastic Liouville equation. Anyway, in the quantum mechanical situation, you have an evolution of the form, you have a Lindblad equation of the form dou rho by dou t, where rho is the density of the density operator of the quantum system. This is minus I by h cross. Then you have h comma rho minus half LL dagger rho plus rho LL dagger minus 2 L dagger rho L. So, this is the Lie bracket between h and rho. We want to derive the Fokker-Planck equation which I wrote above from this equation, and showing that this gives rise to extra corrections in powers of Planck's constant when you try to look at it from the Wegner-Wille distribution viewpoint. But you can go further and also ask the question that suppose you are taking measurements on that Hamiltonian system, noisy measurements on the original classical Hamiltonian system, then you get a Kushner-Kalyanpur equation, and correspondingly this equation will be replaced by a Biliarching filter equation where you have measurement noise terms also coming into account, being taken into account. So, this will represent only the Fokker-Planck part of the evolution of the Biliarching filtered state, and you will have other terms corresponding to measurement noise processes, measurement noise terms. So, let us first look at how the relationship between the quantum Fokker-Planck equation and the classical Fokker-Planck equation, how we can derive one from the other, how we can derive the classical Fokker-Planck from the quantum Fokker-Planck, provided we take into account additional correction terms in powers of the Planck's constant. So, first we note that if we define, you have rho qp, you have rho t qp, this is the let us do it this way. You have rho is a function of t and then q dash, these are the matrix elements of rho t, right, in the q representation, rho t q dash. So, what is the momentum space representation of rho t hat of pp dash? Momentum space representation of this is given by integral pq, then q rho t q dash, then q dash p dash dq dash, which can also be written as up to a taking into a constant proportionality constant to account. This is nothing but rho t of q dash, then e power I pq by h cross into e power minus I p q dash by h cross dq dash, with the normalization constant c chosen so that this becomes a density, that is, it integrates out to 1 when you put p equal to p dash. The trace of rho t and trace of rho t should be 1 whether you look at it either in the momentum representation or in the position representation. That means you require that rho t q dq be equal to integral rho t cap pp dp, and this should be 1. We have already seen that the marginal density, okay, let us now define the Wegner-Wille distribution as rho 1 of qp, rho 1 t, I am suppressing the index t, okay, rho 1 of q and p is defined to be 1 upon 2 pi h cross, 1 upon 2 pi h cross times integral rho of q plus q by 2, q minus q by 2, position representation, position space representation of the density matrix into exponential I pq by h cross dq. If you do this, then if you define the Wegner-Wille distribution, this is a joint density, this should be interpreted as a complex valued joint density of position and momentum. So, what we say is that since there is a uncertainty in p and q of the order of Planck's constant, so over a given box of length h cross in phase space, over a given box of area h cross, you average out the density with respect to position and momentum over this box, and this Wegner-Wille representation, this Wegner-Wille density represents just an average of over each box of area order Planck's constant. So, if you define it this way, and likewise for operators, for observables you define the Wegner-Wille distribution in the same way, except you suppress the 1 by 2 pi h factor down. So, this is defined as x of q plus q by 2, q minus q by 2, then exponential I pq by h cross dq. Then we can write the inverse of these relations, right. The inverse transform of this is, which will give you the density matrix in the position space representation as a in terms of the inverse transform of rho 1, and likewise an observable in the position space representation as an inverse transform of x1. Rho 1 and x1 are now ordinary functions of q and p. x1 qp is to be interpreted as a classical observable as a function of position and momentum. Likewise, rho 1 qp is to be regarded as a joint density of position and momentum in the classical sense, although strictly speaking this interpretation is not correct, because these are not real quantities, but you can show that very easily. If you integrate rho 1 qp over all p, then you will get the marginal density of q, that marginal probability distribution of q, that means you will get rho of qq, you will get the probability density of q, of the q variable you will get the marginal probability density of the q variable, and likewise if you integrate rho 1 qp over all q, then you will get the marginal density of the momentum. It is very easy to show. It's a trivial exercise in integration. So what you can show further is that if you look at trace of rho x, right, this is given by integral rho of q dash x of q dash q dq dash, right. This can also be written as in the Wegner domain as rho 1 of q p x1 of q p dq dp. That is, this corresponds to it is just like how you consider averages of functions of random variables in classical probability theory. X1 qp is to be regarded as a classical observable, namely a function of the random variables q and p, okay, and rho 1 qp is to be regarded as a joint density of the random variables q and p. Although strictly speaking this interpretation does not make sense, because q and p do not have a joint density. You can show it is a trivial exercise in integration to show that that the quantum expectation of an observable can also be viewed upon as a classical expectation of a classical observable, provided you admit complex densities, complex probability densities into the picture. Now suppose you take two observables, say I take a density and I take an observable, and suppose I look at its Wegner transform regarding this as a density evaluated at q and p, then this is equal to rho x of q plus q by 2 q minus q by 2 e to the power I p q by h cross dq integral, which can also be written as integral of rho of q plus q by 2 q dash x of q dash q minus q by 2, then e power I p q by h cross, then dq dash, and then I look at the inverse transform. I substitute for rho, for this matrix rho q plus q by 2 q dash, its expression in terms as an inverse transform of the Wegner-Wilier distribution rho 1, and likewise I substitute for x its inverse transform in terms of the Wegner-Wilier distribution of x. That means what I am saying is when I invert the relation, invert the relation which takes x to x1 and rho to rho 1, when I invert this, x is an operator, rho is also an operator, rho 1 is a complex density, and x1 is a complex valued function of q and p. If you invert the relations which I gave above, then you will get x1 of q comma p is equal to 1 upon 2 pi h cross integral x of q plus q by 2, sorry, it should have been so I have x1 of qp defined in this way, right, q minus q by 2, you do not have this for observables, exponential I p q by h cross dq, you have this. If you invert this, and likewise you have rho 1 of qp is equal to 1 upon 2 pi h cross integral rho of q plus q by 2 q minus q by 2 exponential I p q by h cross dq. If you invert this, you will get x of q dash is equal to 1 upon 2 pi h cross integral x of x1 of q plus q dash by 2 q plus q dash by 2 comma p e to the power minus I p q minus q dash by h cross, then dp, and likewise you will get rho of q dash, the density operator in the position domain, the observable in the position domain, as integral of rho 1 q plus q dash by 2 comma p e power minus I p q minus q dash by h cross dp. So these are the inversion formulas for the Wegner transform, and if you substitute this into this equation, namely trace of rho into x, then you can also write this as then you can show that you can write this as integral rho 1 of qp x1 of qp dq dt. Moreover, you can go one step further, you can compute rho of x1 at qp. Regarding this as a density, then this is defined as rho x of q plus q by 2 q minus q by 2 a to the power I p q by h cross dq into 1 by 2 pi h. So, if you substitute, if you write this as a product of the q as a in the if you use the formula for the product of two operators in quantum theory and you substitute for rho 1 and x1 in terms of for rho and x, their expressions in terms of rho 1 and x1, then you can show very easily that rho x1 at qp can also be written as rho 1 of qp x1 of qp minus IH by 2 times the so you can show that this is the same as minus IH by 2 times minus IH by 2 times rho 1 comma h1, rho 1 comma x1, rho 1 comma x1, the classical Poisson bracket between rho 1 and x1 plus h square by 8 times dou square rho 1 by dou q square, dou square rho 1 by dou q square, dou square h1 by dou q dou p square plus dou square h1 dou square rho 1, dou square rho 1 by dou p square, dou square h1 by dou q square plus 2 dou square rho 1 by dou q dou p, dou square rho 1 by dou q dou p plus order h cube. The idea is very simple in arriving at this formula. You simply note that you simply note that rho of x1 at of course you can also do it for the other way, you can do it for the Hamilton, it is more convenient to do it for a Hamiltonian operator and the density operator, and you are looking at this because in the end we want to get an expression for h comma rho. So if you look at h comma rho h rho 1, the product of these two evaluated at qp as a Wegner density, then this is nothing but 1 upon 2 pi h cross times 1 upon 2 pi h cross times integral h of q it should have been h rho of 1, h rho of 1 that 1 won't be there, you are transforming it. So h rho at q plus q by 2, then q minus q by 2, then e power I p q by h cross dq, which can also be written as 1 upon 2 pi h cross times integral of h of q plus q by 2, then q dash, then rho of q dash, then q minus q by 2, then so the product of these two into e power I p q by h cross dq dash dq, and then I substitute for h its expression in terms of h1 and for rho its expression in terms of rho 1. So I will get that the same thing is equal to 1 upon 2 pi h times. So this is h rho 1 at qp, so equal to this times integral. Here you will get h1 of, you substitute the expression for h1, so you will get okay, you will get H1 of, so q plus q by 2 is replaced. When you have q plus q by 2 comma q dash, so this is nothing but q this is h of q plus q by 2 comma q dash into rho of q dash comma q minus q by 2, or this is h of q plus q by 2, you are multiplying h with rho. So, q minus q by 2 exponential I p q by h cross into dq dq dash, which is equal to 1 upon 2 pi h square times integral. Here it will be h of h1 of q plus q dash by 2 plus q by 4, and then q and then p dash into rho 1 of q dash plus q minus q by 2 minus q by 4, the sum of this by 2, and then the p double dash, and then exponential several terms will come, right. So, you will get exponential minus I p dash into the difference of these two, q plus q by 2 minus q dash. So, q minus q dash plus q by 2, and similarly exponential minus I p dash divided by h cross. So, p double dash divided by h cross times those terms. So, you will get a big expression, right. Let me write down that expression that you will get here. You will get h rho 1 at qp equals, I just write down this expression. So, we will get this expression as 1 upon 2 pi h cross square integral h1 of q plus h xi by 2 p dash, then rho 1 of q plus h eta by 2 p double dash, then exponential I p dash eta into exponential minus I p double dash xi into exponential I p xi minus eta dp dash dp double dash d xi d eta, and then you expand these functions in terms of Planck, in powers of Planck's constant, and retain up to order h cross. So, treating xi and eta as variables of the order of unit magnitude, and then when you use this and combine with the fact that when you have something like xi into e power I p xi d xi, this quantity is nothing but minus I dou by dou p of delta p, and similarly when you have xi square, more generally when you have things like integral xi power n e power I p xi d xi, then this is nothing but minus I dou power n by dou p power n minus I power n into delta p, delta function, just a single variable delta p. Then finally, and when you simplify it, you will get the result that rho h1 of qp is given by h rho 1 of qp is simply given by an expression of the form h rho 1 qp is given by h1 qp rho 1 qp minus IH by 2, the Poisson bracket between H1 and rho 1 at QP, plus H square by 4 pi square times dou square H1 by dou Q square so H square by, this will not be there, this will become H square by 8 times this into dou square rho 1 by dou P square plus dou square H1 by dou P square dou square rho 1 by dou Q square plus 2 dou square H1 by dou Q dou P dou square rho 1 by dou Q dou P plus order H cube. Okay. So, just a formula which you can keep for reference. Like, so if you, now our aim is to get at H comma rho, I want to get a expression for the Wigner-Wille transform of H comma rho 1, H comma rho at QP. So, you do it for H rho 1 and you also do the same thing for rho H1 and subtract, then you will get the resulting expression. What you will get is that H comma rho 1 at QP, the order H square term will cancel out when you take the commutator. So, this will be equal to simply equal to the Poisson bracket between H and rho, H1 and rho 1, the Poisson bracket between H1 and rho 1 QP minus IH cross times so it will be minus IH cross times H comma rho 1, no, this will not come, this will simply be of the form, minus IH cross H comma rho 1 plus order H comma rho 1 cube, order H cube, the square terms in H cross will cancel out. So, this is the major formula which we are looking at. So, if you look at, for example, the Fokker-Planck issue, quantum Fokker-Planck equation or the master equation that reads as minus I by H cross H comma rho minus plus theta of rho, where theta contains, this is the Lindblad term, and so if you take the Wigner-Wille transform on both sides, you will get dou rho 1 by dou t at t QP. The minus I by H cross will cancel out, that will give you minus the Poisson bracket between H1 and rho 1 at QP, and then you will get a theta rho 1 term plus order H terms will come from here, order H square will come from here when you divide by that, plus theta rho of H, theta rho 1 at QP. This will be the Lindblad term. Up to order H square you get with neglect of order H cross square you get this equation which is the classical Liouville equation, but it will become the classical Fokker-Planck equation when you take the Lindblad terms into account, namely theta rho 1 when you express it in terms of the Wigner distribution of rho 1, it will do the work. For example, suppose you take your Ls simply multiplication by a complex function of Q, then what is theta rho? Theta rho at Q dash in the position representation, that will be minus half LL dagger plus into rho, minus half LL dagger into rho plus rho into LL dagger minus 2 L dagger rho L Q dash. So, this will be equal to minus half. If you substitute for this, you will get G square. So, you will get GQ minus GQ dash mod square into rho Q dash plus another term will come which will be of the form minus half this plus I imaginary part of GQ bar GQ dash EQ dash rho Q dash. Right. If you substitute, for example, what will happen is that LL dagger rho, if you look at this term, this whole expression can be written as, the Lindblad term can be written as GQ LL dagger. LL dagger means GQ into G bar Q. G bar Q, GQ into G bar Q plus GQ dash into G bar Q dash minus 2 GQ L dagger, LL dagger. So, G when you look at the term L dagger rho L, so that will be G bar Q into GQ dash, this into rho Q Q dash in the position representation, and you can write this as simply you can write this as GQ minus G of Q dash mod square minus 2I imaginary part of GQ bar GQ dash multiplied by rho Q Q dash, right. Now, when you substitute, when you look at the Fokker-Planck term, say a term like mod of GQ minus GQ dash square, you get minus half of this, and you multiplied by rho Q Q dash, and then you LL dash, and then you take the Wegner transform of this function, then what will you get? You will get G of Q plus Q by 2 minus G of Q minus Q by 2, we get this quantity. So, square multiplied by rho of Q plus Q by 2, Q minus Q by 2 into e power I p q by h cross dq multiplied by 1 upon 2 pi h. So, if you make the substitution of variable q equal to h cross xi and expand in powers of xi, you expand in powers of xi and retain, so what will you get? What you will get is that, and you retain terms up to order h square, you retain terms up to order h cross, right. So, if you retain terms up to order h cross, what you will get is that right. So, if you retain terms, you will get and you expand it, then what you will get is that you will get something like h square by 2 into mod g dash q square into dou square rho 1 q p by dou p square. Similarly, if you look at the other term, imaginary part of g bar q dash, g bar dash of q, g of q, the other term will give you 2 h cross, it will give you 2 h cross dou rho 1 qp by dou p. So, up to order h square you get all these things. This could be regarded as a drift term coming in the Fokker-Planck equation, coming from this extra term, and this is the diffusion term which comes from the quantum Fokker-Planck equation after retaining terms up to order h cross square. So, essentially what you are saying is nothing, you are just saying that you take g of q plus q by 2 minus g of q minus q by 2 mod square, and you are taking rho of q plus q by 2 q minus q by 2 and then exponential I p q by h cross dq, and then you divide this by 1 by 2 pi h cross. So, this is the same as 1 by 2 pi h cross integral mod g of q plus h xi by 2 minus g of q minus h xi by 2 square into rho of q plus h xi, q plus h xi by 2 q minus h xi by 2 into exponential I p xi d xi into h cross. So, that h cross will cancel out here, and you expand this in powers of Planck's constant. So, you will get the first term will be, leading term will be g dash q into h xi by 2 mod square you are getting here into all these other terms, e power I p q rho of q plus h xi by 2 q minus h xi by 2 into e power I p q and so on, and wherever you have a xi square into e power I p xi, that will be replaced by a double derivative of the delta function at p, right. So that will be replaced, no, that will be replaced by not a double derivative, it will be replaced by a derivative with respect to p. That is, if you have a term like xi square e power I p xi, if you have a term like e power I p xi into some function of p like this you are getting, or so some function of xi d xi, you have something like this, right. Then this could also be replaced by minus of dou square by dou p square, dou square by dou p square of e power I p xi f xi d xi. So that is how you get the diffusion term. On the other hand, suppose you have, if you look at the other term, namely gq bar into gq dash, gq bar into gq dash, and then you have imaginary part of this thing, and you are looking at what term this corresponds to, what is the Wegner transform of this, then you will get the drift term which I mentioned. If you go to the Wegner domain, this will become imaginary part of g of q plus q by 2 bar into g of q minus q by 2 multiplied by rho q plus q by 2 q minus q by 2 e to the power I p q by h cross dq, and you make the same substitution, q is equal to h cross xi, and expand, then you will get up to Planck's constant. Of course, you are dividing by 2 pi h cross here, right, to normalize it, then you will get a term 2 h cross imaginary part of g dash q bar gq dou rho 1 qp by dou p plus order h cube, h square term will cancel out, that is how you get the drift term. So in other words, if you take the whole Fokker-Planck equation dou rho by dou in the quantum domain, the quantum Fokker-Planck equation, namely the master equation, plus theta rho, where theta rho is given by minus half LL dagger rho plus rho LL dagger minus 2 L dagger rho L, with L equal to GQ, where G is a complex valued function of Q, and you transform this in the Wegner domain, this reads dou rho 1 TQP by dou T equals minus I minus h cross, that will cancel out, you will get this minus h comma rho h1 comma rho 1 h1 comma rho 1 at TQP and then you will get some other terms. So you will get this plus 2h cross imaginary part of g bar dash at q gq. If you transform this whole equation into the Wegner into the Wegner domain by replacing, wherever you have an operator, you replace it by q plus q by its matrix elements in the q basis, where q is replaced by q plus q by 2 small q by 2, and q dash is replaced by capital Q minus q by 2 into e power I p q by. You take the Wegner transform on both sides, then you will get this equation and retain terms only up to order h square, h cross square. Then you will get this term, and you will also get a term like a diffusion term, namely h square by 2 times mod g dash q square, dou square rho 1 t q p by dou p square. So you get a classical Fokker-Planck equation up to order h square, you get a classical Fokker-Planck equation, and this is the whole story, right. If you can consider terms of higher order than h cross square, so you can go to h cross cube. So it is just like the classical Fokker-Planck equation with where you have a Hamiltonian part, a drift part, and a diffusion part. Okay, so just made a small mistake here. There is a dou rho 1 by dou q missing here. Right here, there is a dou rho 1 by dou p, TQP, a drift term, a diffusion term, and a Hamiltonian term. Of course, the drift term can also be absorbed into the Hamiltonian term because anyway, you do not get linear velocity damping, but linear velocity damping can come in another way by replacing G, instead of GQ if you take Lindblad operators of the form AQ plus BP, then you can get drift terms also, you can get damping terms also in the Fokker-Planck equation. Now we look at the Biliarching filter equation. So in the Biliarching filter you have, when you don't have conservation, don't take conservation process into account, then you have an evolution operator of the evolution equation, Hudson-Parthasarathi evolution equation is of the form this plus LL dagger by 2 times dt plus LdA t minus L dagger dA t dagger multiplied by ut. This is the Hudson-Parthasarathi equation. It satisfies, of course, the quantum Ito's formula used is dat dagger equal to dt, and dat dagger dat equal to 0 equal to dat square equal to dat dagger square, all these are 0. So you are this guarantees unitary evolution, namely du u dagger equal to 0. So if initially it is unitary, then after at any time it will be unitary. So now you look at this Hudson-Parthasarathi equation for ut, take a system observable x and look at its evolution after time t, ut dagger x ut, I call it as jtx, the star unital homomorphism. It is a star unital homomorphism because it is an algebra homomorphism from the algebra of system observables to the algebra of system tensor noise observables up to time t. So it satisfies jt of alpha x plus beta y is equal to alpha jtx plus beta jty, and jt of xy equals jtx jty, and also jt of x star equals jt of x star. It preserves the adjoint. So you then look at a noisy measurement process, namely dyot. So you take an input non-demolition noise as C times AT plus C bar times AT dagger, namely quantum Brownian motion after the appropriate scaling. So of course dyit satisfies the classical Ito rule, namely from the quantum Ito you derive easily that this is equal to this into dt, and you define yot, the output measurement noise, output non-demolition measurement noise, to be ut dagger yit ut. Then we have seen by applications of quantum Ito's formula that dyot can be written as dyit plus dut dagger dyit into ut plus ut dagger dyit into dut. The other terms drop out because of the unitarity of ut. So this can also be written as C times dat plus C bar times dat dagger plus, okay, if you substitute wherever you get such a product, you have, this will contribute a non-zero term only when you take the dat term in dut dagger and the dat dagger term in yit. Similarly, when you take a dat term in dyit and a dat dagger term in ut, it will contribute by virtue of the quantum Ito's formula. So this will be jt of C bar L plus CL dagger into dt. So it is just like measuring a classical observable, namely it is just like measuring a classical observable C bar L plus CL dagger and then adding noise to it. So this is the equation of evolution of yot. You see, in classical measurement theory, what do? You have a stochastic process xt and you measure it, means you measure some function of it plus noise. This is how you do the measurement, right? In classical Kushner-Kalyanpur filter, you write it as dzt is equal to f of xt dt plus dvt, where xt is the state of the system. So if I define the observables to be coming from a commutative Banach algebra of functions defined on the state space, then jtf can be defined as f of xt, where f is a function. These are commuting observables, namely functions defined on the state space of the system, and obviously it satisfies all the properties, namely jtfg is equal to fg of xt, which is equal to f of xt g of xt, g of xt which is equal to jtf jtg g, and it also satisfies the linearity property, and you can and then you filter it out, right. So, this measurement equation can also be written as dZt is equal to Jt of f dt plus dVt, right, where you have a measurement is a function of the state at time t plus the noise. So, our Biliarching filter non-demolition measurement equation is some sort of a generalization of that, where f is replaced by C bar L plus CL bar, CL dagger with a negative sign. So, now when you compute the Biliarching filter, namely you assume that the filter is a real time filter, namely the conditional expectation pi tx is equal to expected value of jtx given eta ot. Eta ot is the sigma algebra formed by the non-demolition measurements up to time t, namely YOS s less than or equal to t. It's an abelian algebra. All families of the family of these observables commutes with each other, and it also commutes with the future state, so that it won't destroy the future state of the system. That is why you are able to construct a conditional expectation. So, if you now of course you expect that the filter is such that when you want to update the estimates at time t plus dt, then you use the estimate at time t, and to that you add an increment term coming from the extra measurement which you have taken on the output process between the time interval t to t, in the time interval t to t plus dt. So, this should be of the form ft of x dt plus gt of x dy ot. Namely, when you take an extra measurement, you have an extra correction to the filter estimate at time t. So, you can say that the filter estimates the state at time t plus dt based on the extra new measurement as the original estimate plus an extra term coming from the incremental measurement over time t to t plus dt. This extra information comes in the form of ftx dt plus gtx dy ot. Right, this is the philosophy of the Kalman filter, of the Kushner filter, of the Kushner-Kalyanpur filter, and so on. When you take an extra measurement, you get an updating of the state estimate, of the estimate of the observable. So, if you assume this, and then you put the relation, and then you use the orthogonality principle, namely jtx minus pi tx, this will be orthogonal to eta ot. So, you get an equation of the form jtx minus pi tx multiplied by Ct is equal to 0, where Ct is in the sigma algebra of the output measurement up to time t. So, if you choose a particularly Ct to satisfy, in particular the Ct is to satisfy a stochastic differential equation of the form ft Ct dy ot, so that it becomes a Volterra series in a chaos expansion in the output observables, and you take the d of this and use Ito's formula, then you will get a formula, and you substitute for wherever you have d pi tx coming, you substitute d pi tx equals ftx dt plus gtx dbt, gtx dy ot, where your ftx and gtx are measurable with respect to eta ot, that is they are functions of the noise process yo up to time t, because it is a conditional expectation given eta ot. So, all this should depend only on the output measurements up to time t. So, if you substitute that, finally you will get the equations. So, you will get two equations for ftx and gtx. I just write down these two equations. These two equations are okay, these two equations are ftx. Of course, all conditional expectations are taken in the state f, in the state of the system and bath, namely phi u and phi u. The bath is in the coherent state phi u, and the system is in a pure state ff, where f is an element of the system Hilbert space. All expectations and conditional expectations are taken with respect to this state. So, you will get an equation for ftx of the form pi t of theta 0x plus pi t of theta 1x multiplied by ut plus pi t of theta 2x multiplied by ut bar minus gt of x times c ut plus c bar ut bar minus pi t of c bar L plus C L dagger. You will get this expression for ftx in terms of gtx, and for gtx you will get the relation, and for gtx you will get gtx is equal to 1 upon mod c square times c bar pi t of theta 1x minus pi t of x times c bar L plus C L dagger plus pi t x into pi t of c bar L plus C L dagger. Right, this is what you will get for GTX. So if you substitute all this into the filter equation, the final form of the Biliarching filter is that the final form of the Biliarching filter is d pi t x equals pi t of theta 0 x plus pi t of theta 1x ut plus pi t of theta 2x times ut bar dt plus gtx times dyot minus cut minus c bar ut bar plus pi t of c bar L plus C L dagger dt. So this is nothing but the Lindblad operator in the coherent state acting on the observable x. Theta 0, theta 1, theta 2 are given by the formulas. Let me just write down what are the theta 0, theta 1 and theta 2. Theta 0, theta 1, theta 2. Yeah. So theta 0, so this is the Lindblad generator acting on the state, acting on the observable time t. In the absence of when the coherent state is a vacuum coherent state, that is ut is 0, then it becomes simply the generator of the Lindblad generator. Pi t of theta 0x in the coherent state, theta 0x, these are all these theta 0x, theta 1x, theta 2x, they are all system observables. When ut is 0, that is you are looking at the vacuum state, you are computing expectations and conditional expectations when the bath is in the vacuum coherent state, then you get just the generator theta ox, pi t of theta ox. So if you take the anyway, now your theta 0, theta 1 are given by theta 0x is nothing but the generator, namely I h comma x minus half LL dagger x plus XLL dagger minus 2 LXL dagger, and theta 1x is nothing but x comma L, and theta 2x is nothing but L dagger comma x. So when there is in the vacuum coherent state, these theta 1, theta 2 terms won't appear in the first part, in the ftx part, only this term will appear, and the other term is a measurement correction term. So now you of course when okay, you make the change c goes to minus c, so that you come the notation is so the notation corresponds to the that is to the Kalman filter notation. So there you get an equation of the form pi tx d pi tx equals pi t of theta 0x dt plus gtx times dyot minus pi t of C bar L plus CL bar, CL dagger dt. So what this says is that pi t C bar L plus CL dagger. You see, you are measuring the observable C bar L plus CL dagger. According to the measurement model, you have dy ot. This is the form Jt of C bar L plus CL dagger dt plus dy it. That means you are measuring the observable. You are measuring the observable C bar L plus CL dagger, and you are taking its conditional expectation at time t. So that is an estimate of nothing but the estimate of the output noise, right. If you know C bar L plus CL dagger, its conditional expectation is an estimate of the output noise dy ot, and you are subtracting that from dy ot, namely you are taking the error between the actual output noise and the estimated output noise, feeding it back into the term gtx and getting a correction to the filtered estimate at time t plus dt of the observable x. This is the natural Fokker-Planck evolution. In the absence of measurement, it will evolve according to the Fokker-Planck equation, namely the master equation for open quantum system. The extra measurement term causes this additional term to come into the picture. So if you write this in the state domain, that means you define the dual, you define rho bt, the Biliarching filtered state, as a function of eta ot, the output measurement algebra up to time t multiplied by x. Suppose you write this as trace of this represents simply pi t of x, right. Pi t of x, this is the conditional expectation of jtx given eta ot. So if you write this in the if you define a Biliarching filtered state in this way, then rho bt forms a commuting family of observables, because they are all measurable with respect to the output measurement sigma algebra at time t, and the output measurement sigma algebra forms an abelian algebra. So you can define it in this way, and you can pass over from the Biliarching equation in the observable domain to from the Biliarching filter equation in the observable domain to the Biliarching filter equation in the state domain by simple application of the duality. Namely, if you have something like say d pi tx, then this will become simply d of trace of rho b t into x, which is trace of d rho b tx. Likewise, when you have something like pi t of theta 0 x, this can be written as trace of rho b t times theta 0 x, which is equal to trace of theta 0 star acting on rho b t multiplied by x. Like that you can pass over to and then equate coefficients of x on both the sides. So you get an equation for the Biliarching filtered state in the following form. You get d rho b t is equal to minus I by h cross h comma rho b t dt minus half LL dagger rho b t plus rho b t into LL dagger minus 2 L dagger rho b t into L. You get this into dt. This is the Fokker-Planck part, free evolution in the absence of any measurement, plus an extra term which is the measurement term, namely rho b t multiplied by m plus m dagger multiplied by rho b t minus trace of rho b t into m plus m dagger multiplied by rho b t, whole thing multiplied by dy ot, the measurement output measurement error minus trace of rho b t multiplied by m plus m dagger dt. So this is the Biliarching filter equation in the state domain. The rate of change of the state is equal to the open system generator acting on rho b t, as you do in the conventional master equation or GKSL equation for open quantum systems with an extra measurement term. Now when you take the Wegner-Wille distribution transform on both sides and look at what happens in the how does the Biliarching filter state look like when you interpret rho b t as a Wegner-Wille density, joint density of position and momentum for the Hamiltonian system, then what will happen is that you define rho b1 of t qp the usual way. You define it as rho b t q plus q by 2 q minus q by 2 e power I p q by h cross dq divided by 1 by 2 pi h, and likewise you do it for every term. Then what happens is that when you take a thing like say trace of rho b multiplied by m plus m dagger. Okay, this term is going to be nothing, it is going to give you simply rho b 1 at t q p into m 2 real part of m1 at q p dq dp, because the Wigner-Ville transform, if you look at the Wigner-Ville transform of m dagger 1 at qp, it is nothing but m1 of qp bar. You can see it very simply. So this will become simply an ordinary expectation in classical probability theory, but when you look at the terms like rho m, rho bm plus m dagger rho bt, you look at this term, when you look at the term this, then this will become, in the Wigner-Ville domain, this will transform to rho bm plus m dagger rho b 1 at qp, and this, as we saw, is given by rho b, it will be 2 real part of m at qp into rho b 1 at qp up to order h cross, and when you take the h cross term into account, you will get a commutator, namely you will get a minus ih cross by 2 times a classical Poisson bracket, namely rho b 1 comma m1, and here you will get a minus ih cross by 2 times an m1 bar comma rho b 1, a Poisson bracket you will get, and these two, of course this is the negative of this with a conjugation, so the sum of these two terms can be written as minus ih cross by 2 times rho b 1 comma m1 minus m1 bar, which is 2i imaginary part m1, 2i, and this will cancel, this will become h cross into rho b 1 comma m1 real part of m1. So let me write it properly, minus h cross times minus h cross by 2 times rho b 1 comma imaginary part of m1, that is, this extra imaginary part of m1 appears with a Planck's constant as a correction term to the Biliarching filter. You are measuring here, here m1 is an observable, m is the observable, c bar, I think it is cl, right, c bar l is the observable being measured, is the observable which occurs in the Biliarching filter, and so you will get an extra imaginary m1 term which occurs, which is not there in the classical Kushner-Kalyanpur filter. In the classical Kushner-Kalyanpur filter, you get only real part of m1, namely real part of m1 qp, right. So if I write down the complete filter, if I write down rho bm plus m dagger rho b, this 1 at qp, I am ignoring the argument qp, then this is nothing but rho b1 into 2 real part m1 minus ih cross by 2 minus ih cross by 2 no, just 1 minute. Let me see, rho bm plus m dagger rho b at 1 at qp. Yeah, this is equal to rho b1 at m1 plus m1 bar minus ih cross by 2 Poisson bracket between rho b1 comma m1 minus m1 dagger m1 bar, that will give the imaginary part of m1, this gives the real part of m1 plus h square by 4 times dou square rho b1 by dou q square into dou square real part of m1 by dou p square plus dou square rho b1 by dou p square into dou square real part of m1 by dou q square plus 2 dou square rho b1 by dou q dou p into dou square real part m1 by dou q dou p. You get an order h square correction term also into this equation. So when I write down the complete equation, the Biliarching filter in the Wegner domain up to orders h square in Planck's constant, up to order h square in Planck's constant, the Biliarching filter equation, let me write it down, Biliarching equation in Wegner domain, up to order h square. So it looks like just the Kushner-Kalyanpur filter with extra h and h square terms coming into the picture. It is d rho b1 t q p equals minus of h1 comma rho b1 plus L acting on rho b1 dt. This is the Fokker-Planck term. These are the diffusion and the drift terms which come into the picture, namely h cross times a diffusion term and a drift term, right. So this L corresponds to something like what we got when you took, so it had a dou by dou p term and it had a dou square by dou p square term, right. In the Fokker-Planck equation we had got this term, these two terms, earlier we had derived them. So this came from by taking the Lindblad operator as g of q, then you got a term like imaginary part of g dash bar at q gq multiplied by dou p of rho 1, that corresponds to the drift part in L. Likewise you had a g dash of q square into of course h cross, and then h cross square times dou square rho 1 by dou p square, both of these came in L. You had this term plus 2 rho b1 into real part of m1 plus h cross times rho b1 comma 2 imaginary part m1, right, this plus h square by 4 times the second order term in rho b1 minus twice rho b1, you will get the measurement terms also into the picture, right. So okay, let me write it down clearly showing the correction terms which come. D rho b1 is equal to minus of h comma rho b1 plus L rho b1 into dt plus 2 rho b1 into real part of m1 minus 2 integral rho b1 into real part of m1 dq dp multiplied by dyo minus 2 integral rho b1 real part of m1 dq dp. This is the usual Kushner-Kalyanpur equation when you measure real part of m1. Plus where L has the diffusion and the drift terms of order Planck's drift term is of order Planck's constant and diffusion term is of order Planck's constant square, right. Or when you that is the way it is, plus an extra correction term, namely coming from quantum effects. So that will be the extra correction terms will be h cross plus h cross times rho b1 comma twice imaginary part of m1. This imaginary part of m1 is special to quantum theory, it does not occur in the Kushner-Kalyanpur equation, plus minus 2 real part rho b dq dp multiplied by rho b1, this multiplied by rho b1. Okay, this multiplied by rho b1. This is the Kushner-Kalyanpur equation when you take rho b1 as the conditional density of the state at time t given measurements up to time t, and you are measuring the observable 2 real part m1. So, this plus 2 imaginary part of m1 times into h cross, then you will have plus h square by 2, h square by 4 times dou square rho b1 by dou q square into dou square real part m1 by dou p square plus dou square rho b1 by dou q square into dou square real part of m1 by dou q square. Dou square real part, here it is dou p square, right, dou square real part rho b1 by dou p square, okay, plus 2 dou square rho b1 by dou q dou p into dou square real part m1 by dou q dou p. This whole thing times dyo minus twice integral rho b1 real part m1 dq dp times dt. So, the same term, the same measurement term which you get here, you will get here into measurement noise term, but these are extra corrections in powers of Planck's constant. You have an extra h cross, you have an h cross square here, and in L you have an h cross coming from the Lindblad drift term and the Lindblad diffusion term. So, this is the complete picture of the Kushner-Kalyanpur of the Biliarching filter up to order h square, and you see that up to order h power 0 it is same as the Kushner-Kalyanpur equation. The extra h cross comes from measurement effects as well as imaginary part of m1, the observable being measured. Okay. So, today I shall explain to you how when the permittivity and permeability within a waveguide or within a resonator cavity become functions of frequency and space and time coordinates, then how the oscillation frequency in a resonator will get shifted. Using perturbation theory I will make a small calculation. So, the idea is that if you use, let us say you have a resonator like this, a resonator cavity, this is the xy plane, this is the xy plane and this is the z axis. So, it stretches from z equal to 0 to z equal to d, and the Maxwell equations are curl of E is equal to minus j omega mu h and curl of h is equal to j omega epsilon E, where mu and epsilon are functions of space and time coordinates. So, epsilon is a function of omega x, y and z, and mu is also a function of omega x, y and z. To start with, we shall assume that epsilon and mu do not depend on z, they depend only on x and y. So, we shall assume this special case to start with, and let us see how we can generalize this. The calculation is based on perturbation theory for eigenvalue problems in partial differential equations, like how we calculate the shift in the energy levels of an atom when it is perturbed by a small potential using time independent perturbation theory in quantum mechanics as described in Dirac's book. We shall apply a similar idea here and arrive at the shift in the formulas for free shift in the frequencies of oscillation. So, you have this and you assume that epsilon is a small perturbation, epsilon 0 plus into 1 plus delta times chi e of xy, omega xy. Likewise, you assume that mu is a small perturbation of a constant, namely delta times chi m of omega xy, where chi e omega xy is the electric susceptibility and chi m omega xy is the magnetic susceptibility. So, if you look at these two equations and you assume a dependence of E and H on z as e power minus gamma z, so that dou by dou z gets replaced by multiplication with minus gamma, then we have already seen that you can write down the transverse part of the electric field, namely that part which lies in the xy plane as minus gamma by h square del perpendicular E z minus j omega mu by h square del perpendicular h z cross z cap, and likewise h perpendicular is equal to minus gamma by h square del perpendicular h z plus j omega epsilon by h square del perpendicular E z cross z cap. It comes by simply manipulating the two curl equations, the two Maxwell curl equations. Now, if you look at h square, what is h square now? H square will be the same, it is omega square mu epsilon plus gamma square, but this is no longer a constant because epsilon and mu depend now on omega x and y. So, what I do is I write down h square as omega square epsilon naught mu naught into 1 plus delta chi e of xy of omega xy multiplied by 1 plus delta times chi m of omega xy, okay, plus gamma square. So this is nothing but omega square epsilon naught mu naught plus gamma square, this is a constant, plus delta times, say I write it as omega square mu naught epsilon naught times some function of x and y, delta times, where this function is a product, this function f is given by chi e, of course it will also depend on omega. So it is chi e plus chi m plus delta chi e chi m, that is what this function is. This quantity is a constant because gamma is a constant and epsilon, mu naught and omega are also constant. So this can be written as h0 square plus delta times k square times f of xy, f of omega xy, where k square is nothing but omega square epsilon naught mu naught, which is nothing but the which is k square. K is nothing but the wave vector in vacuum or in the absence of any or in a constant medium having permittivity epsilon 0 and permeability mu 0. So this is a small perturbation term which will cause a shift in the frequencies. Let us see how it comes. So you write down E perpendicular as is a function of omega x and y as minus gamma by h square. Now h is a function, h square is a function of omega x and y as we just saw, and then del perpendicular Ez minus j omega mu by h square into del perpendicular hz cross z cap, and likewise you have h perpendicular is equal to minus gamma by h square del perpendicular hz plus j omega mu by h square del perpendicular Ez cross z cap, and then you substitute this into the third Maxwell curl equation, namely curl of E perpendicular is equal to minus j omega mu hz into z cap, and curl of h perpendicular is equal to j omega epsilon Ez into z cap, where now u and epsilon again depend on x and y. You substitute this, you cannot take now, you cannot say that the curl of this quantity is 0, right, because curl, if you look at the curl of this quantity, you will get curl of gamma by h square into del perpendicular Ez. So this will become minus gamma, you are looking at del perpendicular, right, not curl, you are looking at the del perpendicular cross this. So sorry, this should have been del perpendicular cross, del perpendicular cross, del perpendicular cross. This is the third Maxwell equation. So when you look at this, this is nothing but del perpendicular 1 by h square cross del perpendicular Ez, because del perpendicular cross del perpendicular is 0, right, del perpendicular cross del perpendicular of any psi is 0. So you will get an extra term, namely gradient of this cross this. Likewise you will get a, when you calculate curl of this quantity, right, you will get similarly del perpendicular of mu by h square, you will get a term like del perpendicular mu by h square cross del perpendicular Ez when you calculate the curl of this portion. So it won't cancel out. In the uniform case these two terms cancelled out and you got a simple equation, namely del perpendicular square. In the uniform case you had del perpendicular square plus some h naught square acting on Ez hz, that was 0. In this case those two, there will be inhomogeneous terms which will appear into the differential equations. So let us see. Okay, so what you are going to do is, if you write down the equation, the resulting equations, you will get del perpendicular square plus h square, del perpendicular square h square acting on Ez hz. You can combine them into this form, Ez hz plus you will get a term like f1, it will be a matrix, it will be a function of omega, and I am expressing everything in terms of h naught square, right. So it will be wherever you have a gamma coming into the picture, you can replace it, since gamma square plus omega square mu naught epsilon naught is equal to h naught square, or equally gamma square plus k square equal to h naught square. You can replace gamma by square root of h naught square minus k square. So and h square is what? H square is nothing but h naught square plus k square times delta k square times f of x y, small f of x y. So, you have to replace that here. Here you will get some h naught, which is a function of h naught is a function of omega, right. So, h naught square, let us call it as h naught square itself, and it will also depend on x and y into dou by dou x plus f2 of omega h naught square xy into dou by dou y acting on Ez hz. Ez hz, this is 0. The partial differential equations which you will get will have this form. I just need this. Okay. So, what is happening is this will contain the inhomogeneous terms. So, you can write this equation also in this form. If you club the equations for E z and h z together, you will get del perpendicular square plus h naught square plus delta times k square into f of x y, f of omega x y, okay, into f of omega x y. This acts on psi x y, psi x y plus f1 of, now this will be omega h naught square x y dou by dou x acting on psi plus f2 omega h naught square x y acting on dou psi by dou y is 0. So, in the inhomogeneous case you will get this sort of an equation where f1 f2 are 2 cross 2 matrices and psi is a 2 cross 1 vector of Ez and Hz. Now, there if you look at the unperturbed case, the case in which the medium is homogeneous, then of course these terms you could put a delta here, it will occur with a perturbation parameter delta. When delta is 0 you get the homogeneous case. When there is inhomogeneity in the medium, then we see that, for example, if you look at del perpendicular of 1 upon h square, that will be of order delta. That is because this can be written as 1 upon h naught square plus delta fxy. So, h naught square is a constant, so this is minus delta del perpendicular f by h square, which is of order delta, and that is why you get a delta term here. When you look at del perpendicular of mu, that will also be order delta, because this will be mu is mu naught into 1 plus delta chi m. So, this del perpendicular of mu is delta times del perpendicular chi m into mu naught, like that del perpendicular of epsilon is also order delta. So, let us see how we can determine the shift in the frequencies using time independent perturbation theory. So, the idea is that initially you start with a mode h0n square, and you let it get perturbed slightly. When you look at the unperturbed equation, the unperturbed equation is del perpendicular, you are expanding psi as psi 0 plus delta psi 1 plus order delta square. So, when you look at the unperturbed equation, it is del perpendicular square, and you put h naught square is equal to some h0, let us say the nth mode, h0n square plus some delta h0n square. Okay, you put that is the shift. So, the unperturbed equation is h0n square acting on psi 0 is 0, and you get all the modes here, right. For each h0n you will get a mode psi 0n. For example, of course that could be a degeneracy. For example, in the case of a rectangular cavity resonator, the transverse electric and transverse magnetic have the same values of the modes, but it is not so in a cylindrical cavity. In a cylindrical cavity, the transverse electric and transverse magnetic have different modes h0n, because the transverse magnetic mode will depend on the modes for the transverse electric case will depend on the zeros of the Bessel function, whereas the modes for the transverse magnetic case will depend on the zeros of the derivative of the Bessel function. So, that is the difference between rectangular and cylindrical cavities. So, you solve the unperturbed equation with some degeneracy, and you are also taking into account the fact that since it is a resonator cavity, right, you require that E perpendicular be 0 when z is 0 and d, and you also require that hz be 0 when z is 0 and d. So, these requirements translated to the requirement that Hz is 0 when Z is 0 on D for perfect electric conductors, and dou Hz by dou Ez by dou Z, that is 0 when Z equal to 0 on D. This means that Hz, the dependence of Hz on Z will be of the form sin pi p Z by D, and the dependence of Ez on Z will be of the form cosine pi p Z by D, where p takes integer values. So these are the boundary conditions, and when you solve them, when you solve the del perpendicular square plus h0 n square acting on psi 0 n equal to 0, you get different modes, and you can include. So for example, the transverse electric modes will be characterized by or the transverse magnetic modes will be characterized by only an EZN and a 0, and the transverse magnetic modes will be characterized by 0 and HZN, right, and they will have in general different frequencies, but in the rectangular waveguide case they will have the same frequencies. So you solve them with some degeneracies, and you should actually put psi 0 n at p, here also h0 n at p. Actually you should put z0 n at p, you are putting psi n here, but h0 n. Okay, now you look at the oscillation frequency. How does it come? It comes from the relation omega square mu naught epsilon naught plus k square, sorry, plus gamma square equals h0 n square, h0 square. So h0, and you also are putting the requirement that gamma is of the form plus or minus j pi p by z, j pi p by d, because the dependence on z is either of the form cos p by z by d or sin p by z by d. So you can write this equation in the form plus mu naught epsilon naught minus pi p by d square is equal to h0 square, h0 n square in the unperturbed case. In other words, the frequencies of oscillation are omega np, which is equal to square root of pi p by d square plus h0 n square divided by root mu naught epsilon naught. These are the characteristic frequencies of oscillation, and you determine the modes using this equation. So different n's in the case of a rectangular cavity, n is parameterized by two indices, namely n and m. So you have a sin n pi x by a, sin m pi y by b, dependence of the electric field Ez on x and y, dependence of magnetic field on x and y is cos n pi x by a, sin n cos n pi x by a, cos m pi y by b, like that. So this n parameterizes the two integers. In the case of a cylindrical waveguide, again you have cos m phi or sin m phi dependent on phi, and j m of some alpha n z, where alpha n are the zeros of the Bessel function or the zeros of the derivative of the Bessel function. So there also the characteristic frequencies of oscillation depend on two integers, right, one determining the Bessel function, or equivalently the phi dependence and phi dependence of the field, and the second integer giving the zeros of the Bessel function or the zeros of the derivative of the Bessel function. So you have this sort of a situation. Now when you perturb it slightly, and there is also a degeneracy, that is for the same h0 n you may have several solutions. So for a given h0 n square, I will say that the eigenvectors are, say, u n k equals 1 2 etc. dn, where dn is the degeneracy. So these are the solutions, and you expand your psi n 0 as, so you can expand psi n 0 as summation cnk unk of xy, k equals 1 to dn. The degeneracy is of 2 for a rectangular waveguide, for a circular waveguide maybe it is 0, but still in general you may assume a degeneracy of dn and try to solve this problem. So what happens when you look at perturbed fields? When the perturbation takes place due to non-uniformities in the permittivity and permeability within the resonator. So you write it as h0 n square plus delta h0 n square acting on psi 0 n plus let us call it as psi 1 n. So psi 1 is a perturbation into delta, and that plus delta times F1 into dou by dou x plus F2 into dou by dou y, acting on psi 0 n plus delta psi 1 n. This is 0. So, since you are looking at the zeroth order term, that is obtained by putting delta equating coefficients of delta power 0 on both sides, is simply the standard Helmholtz equation, 2-dimensional Helmholtz equation for psi 0 n. If you look at the order delta term, here you will have to delete delta psi because this is already of order delta. So, if you look at the order delta term in this equation, order delta term, that is the first order perturbed equation, you will get this plus h0 n square acting on psi 1 n. So, it will be psi 1 plus delta h0 n square, delta h0 square, let us call it as delta h0 square acting on psi 0, like this acting on psi 0 plus f1 is a function of omega. Okay, omega has to be put as the unperturbed frequencies of oscillation, namely omega 0 n, namely omega 0 of n and p, right. Omega 0 n p was nothing but 1 by root mu 0 epsilon 0 into pi p by d square plus h 0 n square power half. So, that you put omega as that here, omega as that, but you are going to, if you are not going to, you actually omega gets perturbed by a small amount of order delta. Since it already multiplies by delta here, the order delta term will not contain those perturbations, they will go into the order delta square equations. So, now if you look at f of omega comma likewise h0 square, h0 n square and then xy into dou psi 0 by dou x plus f2, this matrix, this is a vector, a 2 cross 1 vector, f0 omega h0 n square xy into dou psi 0 by dou y, this is equal to 0, and in this equation I am going to substitute psi 0 is equal to summation c n k into u n k into u n k of xy, k equals 1 to dn, where u n k is there are where the unperturbed solution has a degeneracy of dn and c n k's are some linear combination coefficients. So, if I take the matrix elements on both sides with u n m, okay, u n m these are also 2 cross 1 vector valued functions of x and y. You take the inner product with u n m on both the sides and use the fact that del perpendicular square with the boundary conditions integrates out to act on u n m, that is it, by integration by parts you can transfer the action of del perpendicular square to its action on u n m. So, it will become this side will become what? It will become h0 n square minus h0 m square, just as you have in standard time independent perturbation theory, into u n m comma psi 0. What is that psi 0? That psi 0 is sigma c n k so h0 n, just let me write it down again, okay, I will just write it, del perpendicular square plus h0 n square acting on psi 0 n. So, this was this acts on psi 1. So, this acts on psi 1 and you are taking the inner product with u, let us say ums with some other solution. So, del perpendicular square will go to this side, this will become del perpendicular square ums, okay, plus h0 n square into ums comma psi 1, because of the boundary conditions that other terms will not contribute. So, this will become h0 n square minus hms square into ums comma psi 1, right. In particular, if you put h0 n square, h0 m square this should be, okay, ums, this is h0 m square into ums comma psi 1, and the other term will give you plus delta h0 square delta H0 square times it came with a factor of delta H0 square. You had a delta H0 square plus delta times k square, delta times k square times fxy, f omega xy, or you could substitute this as delta times f of omega xy, like that. So the other term was delta H0 square times ums comma psi 0, which is nothing but sigma c n k u n k over k going from 1 to dn plus delta times here you will have ums comma f, then sigma c n k u n k right, plus the other term. So if I write down in particular, so if I choose m equal to n, then I will get an equation, a secular equation for delta H0 square. Namely, delta H0 square will come out to be the set of eigenvalues of an n cross n matrix, So if you take n not equal to m, then you will get equations for the inner product between the perturbed wave function or the perturbed field and the basis functions from which you can calculate psi 1. So the idea is, if you choose n not equal to m, anyway first choose n equal to m. If you choose n equal to m, then the term will drop out, the first term will drop out, namely you will have here you will have, we are taking the inner product with uns and then del perpendicular square plus H0 n square acting on unk. So that gives you 0. No, this is acting on psi 1, this acts on psi 1, this is 0 because del perpendicular square acting on uns is h minus H0 n square, whereas that will cancel out with a plus H0 n square. So this will give you 0. The second term, what was the equation? The equation was del perpendicular square plus H0 n square plus delta H0 square plus delta fxy, f omega xy, acting on psi 0 plus psi 1, right, where the delta f came by expanding, by noting that H0 square or h square is equal to H0 square plus delta f omega xy, where your fxy was nothing but chi e plus chi m plus delta into chi e chi m. So if you look at the delta, the order delta term in this, what is it? If you look at the order delta term here, this term will not contribute anything. So you are taking the inner product with uns, so it will become simply delta times uns comma f into psi 0, which is unk into sigma c n k summed over k going from 1 to dn. So you will get a matrix multiplied by this vector coefficient cn1, cn2, cn dn, and likewise when you look at the this term plus delta H0 square, then uns comma and I am taking psi 0 to be sigma c n k unk. So that will give you are taking psi 0 to be summation c n k unk summed over k. So that will be plus delta H0 into sigma into c n k. So it will be c n k and then delta sk, because uns is orthogonal to unk. So uns comma unk is equal to delta sk. That is because the eigenvalues, the eigenfunctions of a Hermitian operator are mutually orthogonal. So the unperturbed basis functions which satisfy the unperturbed Helmholtz equation, they will be orthogonal to each other. So you will get this into delta sk, plus you will get a term like summation c n k, here going from 1 to dn, and then here you will have uns with dou f1 by dou x, sorry, it will be f1 dou by dou x, f1 dou by dou x plus f2 dou by dou y, f2 dou by dou y acting on u n k into c n k. So, the sum of these terms is 0. So, you can see that this is a matrix which depends on the frequency, because f1 and f2 they depend on the frequencies through the modes as well as independently also, because the susceptibilities depend on the frequency. So, this is in the form, if you arrange this as a column vector, namely if you arrange c and k as a column vector, k goes from 1 to dn, then this equation can be written in the form, say some a1 acting on a1 as a function of omega, a1 as a function of omega, and also it is a function of h0n. So, h0n square, h0n square, h0n square acting on c and k, acting on c. So, I call this as cn, this vector I call as cn. So, this acts on cn, and this is equal to delta h0 square, the shift in the frequency, shift in the modes multiplied by cn. This can be arranged in this way, right? This equation, I remove this, let us say, where A is the matrix which I had mentioned just now. So, A is the matrix given by, it is a dn cross dn matrix, dn cross dn matrix, it is given by uns comma f1 dou by dou x plus f2 dou by dou y acting on u n k, this matrix, minus the matrix ums comma f acting on u n k. Just try to understand whether this equation is correct or not. Eigenvectors also get perturbed slightly. So, you have expanded your the term dropped out, h0 square delta h1 square when you multiplied by h0, right. So, this is a sort of equation that you will get, right, and delta times h0 square, delta times h0 square, actually you should write it as h1 square. Let me just be clear about it, just see what is happening. You are having del perpendicular square plus h0n square plus delta times h1 square. I am writing h0 square as h0n square plus delta times h1 square, right. I am going to evaluate h1 square plus delta times you have f, which is a function of omega x and y. This acts on psi 0 plus delta times psi 1. When you pick out the psi 1 order delta term in this, so you get del perpendicular square plus h0 n square acting on psi 1, acting on psi 1, you get this, plus h1 square acting on psi 0, right, plus f times psi 0 is equal to f1 dou by dou x plus f2 dou by dou y acting on psi 0, where psi 0 was given by summation c n k u n k summed over k going from 1 to dn. That is a linear combination of the nth mode basis functions correspond with having a degeneracy of dn, and then I took an inner product on both sides with usk, with uns, then this term vanished, the first term vanished, the second term gave you h1 square times something, right, and here you have f comma something, here you have f psi 0 comma uns, here you have this whole vector inner product with uns. So it is correct, right. What you will get is that you will get an equation of the form A acting on omega, and your F1 depended on H0 where you had to put H0n. So you put H0n square in that place acting on this, and that acts on psi 1 or that acts on Cn. So that acts on Cn to give H1 square multiplied by Cn. So the possible eigenvalues of possible solutions for H1 square are what? The shift in the mode. What are the possible solutions? The solutions are given by determinant of A omega comma H0n square minus H1 square into I dn, dn cross dn identity matrix, this is 0. If you solve this determinantal equation, you will get how many roots in general for H1 square? You will get dn roots, right. So these dn roots I will call as H1, for a given n you will get dn roots. So I can call them as H1 n m square, where m takes the values 1, 2, etc. dn. So this is the change perturbation in the modes, and then you want to determine the perturbation in the frequency, corresponding perturbation in the frequency. Remember what was omega? Omega was omega 0 np, right. So you simply substitute what is the change. Omega gets changed to omega plus delta omega, omega plus delta omega square into mu naught epsilon naught plus plus hn square, no, plus gamma square. What was the gamma square? Gamma square was simply minus pi p by d, pi p by d square, and that is equal to h0 n square, h, this is h square, which is h0 n square plus delta plus h1 delta into h1 square, h1 square, where h1 took the values h1 nm, right. And so if you expand this equation, let us call this as delta into omega 1, okay. Let us call the perturbation in the frequency as delta into omega 1. So you equate coefficients of delta on both sides. If you equate coefficients of delta power 0 on both sides, you simply get the unperturbed equation, namely omega square mu naught epsilon naught square minus pi p by d square is equal to h0 n square, which is obvious. This was the unperturbed frequency. The perturbed frequency, if you equate coefficients of delta on both sides, will give you 2 delta into delta omega into omega 1 into omega 1 2 omega into omega 1 into mu naught epsilon naught, then here you do not get, is equal to h1 square. And what is h1 square? h1 square is h1 nm square, h1 nm square. And what is omega? Omega is omega 0 np. So you get the perturbation in the modes as omega 1 delta times omega 1. Delta times omega 1 is the perturbation in the frequency, and that is given by simply h1 nm square divided by 2 into, of course, delta h1, you had the delta and delta will cancel out. So 2 into omega into mu 0 epsilon 0, 2 mu 0 epsilon 0, so into delta. So the perturbation in the frequency is given by this, where omega is omega 0 np, given by this equation, right. This is omega here is omega 0 np, right. So you can calculate the perturbation in the modes in this way. A more complicated problem will be the situation when the fields depend on z also. For example, if you have, when your epsilon is a function of omega x, y and z, and the permeability is also a function of omega x, y and z, then how do you tackle the situation? So the answer to this is that you expand epsilon as a Fourier series in z. So it is epsilon n omega xy e to the power minus j n beta z, n varying over all integers. This is epsilon omega x y z. Likewise, you take mu of omega x y z, you expand this also as a Fourier series, n varying over all z, mu n of omega x y and z e to the power minus j n beta z, where beta is 2 pi by d, d being the length of the waveguide of the resonator cavity. And then likewise you expand the fields. Of course, you should also put a, if you want, you do not put a gamma, you can expand it as a Fourier series. You expand the fields in the same way. So if you look at, for example, the electric field E of x, y, z, that can be written as summation En x, y, of course depends on frequency also, into e power minus gamma plus j n beta z, n varying over z, where gamma is a propagation constant, and you expand this in this way, right. Similarly, you expand h x y z also in the same way. The magnetic field as summation n varying over all z h n x y e to the power minus gamma plus j n beta into z. Expand this in this way, and you substitute into the Maxwell curl equations, namely curl. What is curl? Curl of E is nothing but del perpendicular plus z hat dou by dou z cross E perpendicular plus E z into z cap, okay, and that is equal to minus j omega mu into h perpendicular plus h z, and equate likewise for the second curl equation, that is this is for Faraday's law and likewise for Ampere's law. You expand it and equate coefficients of the same dependence, having the same dependence on z, that is equate coefficients which depend on gamma plus n beta into z, j n beta into z, equate coefficients. So for example, here if you expand, if you look at the perpendicular components, you will get what? You are, when you have mu is expanded as a Fourier series in z, h perpendicular also has a Fourier series. So when you multiply two Fourier series, the corresponding Fourier coefficients will be a convolution of the two Fourier coefficients. So if you equate that, what do you get? You get something like del perpendicular En z cross z cap del cross E plus z cap plus minus z cap del cross E, you get this plus z cap cross dou by dou z of E will have a dependence of minus of, it will have a dependence on z of minus of gamma plus j n beta, okay, this into E perpendicular, En perpendicular, En perpendicular, okay. So this, see, you have del cross, you have del perpendicular plus z cap dou by dou z cross E perpendicular plus z cap E z, right. So if you look at this term, z cap cross dou E perpendicular by dou z, z cap cross z cap is 0, right. So you will, and if you differentiate E perpendicular, what is the nth Fourier component? It depends on z as gamma plus e power minus gamma plus j n beta. So gamma plus j n beta into E perpendicular n. It will have the Fourier coefficient of the coefficient of e power minus gamma plus j n beta z will be this one. So you will get this sort of a thing, right. So what you will get is that del perpendicular E n z cross z cap minus gamma plus j n beta del perpendicular, or it will be simply z cap cross E perpendicular n. E perpendicular n is equal to minus j omega mu h, you have to take the perpendicular part. So that will be minus j omega into summation, if you take the coefficient of e power minus gamma plus j n beta z, here you will get mu m into h perpendicular n minus m summed over all m varying over z, right. Similarly, by duality, if you can get the other equation by duality, let E go to h go to minus E, and epsilon and mu you interchange. Then what do you get? You get del perpendicular h n z cross z cap minus gamma plus j n beta into z cap cross h perpendicular n. H perpendicular n is equal to j omega summation epsilon m into E perpendicular n minus m summed over m. It is a convolution of the two Fourier coefficients, namely epsilon m are the Fourier series coefficients of epsilon, and E perpendicular n minus m is n minus mth Fourier series component coefficient of E perpendicular. So you get this, and then you assume that to apply perturbation theory, you have to assume that the permeability and permittivity, although they depend on Z, their dependence is very weak. So in other words, first you note that your epsilon m depends on omega x and y, and likewise mu m also depends on omega x and y, and you assume that epsilon 0 is dominant, mu 0 is dominant, the other terms are less dominant. To show that, that is, we are assuming that it depends only weakly on Z, that is, the other coefficients are small. You assume that mod of epsilon m is much smaller than epsilon 0, and mod of mu m is also much smaller than mod mu 0 for all m not equal to 0. So you can apply perturbation theory to these two equations. What you do is you simply take z cap cross on both sides, you try to express E perpendicular n and H perpendicular n in terms of del perpendicular E n z and del perpendicular H n z, and then substitute them into the third Maxwell equation, namely del perpendicular cross E n perpendicular or E perpendicular n, whichever way you feel like. You can say E n perpendicular or E n perpendicular n, both are the same. So the nth Fourier coefficient of this is equal to minus j omega z cap times H minus j omega mu. So minus j omega z cap times mu, so mu into H. So it will give you mu m of xy into H perpendicular n minus m summed over all m, and likewise del perpendicular cross H n perpendicular is equal to j omega z cap times, sorry, it should have been z, this should have been, it will be H n minus m z, the z component of H n minus m. Okay, likewise this will be equal to summation epsilon m E n minus m z, or it is better to write it as E z n minus m, because you are using the same notation everywhere, right. You should write it as H z n minus m, and this is E z, this is E z of n minus m at n minus m. So if you substitute this into these two equations, you will get a big equation satisfied by these coefficients H z n and E z n. After eliminating the perpendicular components using perturbation theory, and then you can calculate using standard perturbation theory the shift in the frequencies by assuming that the unperturbed term does not contain epsilon m for m not equal to 0, neither does it contain mu m for m not equal to 0. So for this unperturbed situation, you solve for the resonant frequencies within the cavity using standard methods, and then you apply perturbation theory to solve these equations when your epsilon m and mu m for m not equal to 0 are present. These are all functions of x and y, right. So you have to apply a perturbation theory in two stages. First, for the 0th order term, you get a function, you get your epsilon, you get only epsilon 0 and mu 0 which are dependent on x and y, and so you can solve using the method which I had illustrated earlier by applying perturbation theory to that component epsilon 0 and mu 0 which depends only on x and y to get the unperturbed set of frequencies, and then you apply the second stage of perturbation theory in which you improve upon these estimates by taking epsilon m and mu m for m not equal to 0 into account. So that is all I would like to conclude at this point. Thank you.